Good morning. In the last lecture, we discussed about tautology, contradiction. In fact, contradiction is nothing but fallacy. So this should have been contingency. Now, what is the meaning of tautology, contradiction, that is fallacy and contingency? A statement pattern in which all the entries in the last column of its truth table for all what can we say, for all the truth values of its constituents, components, is called as tautology. That is a statement pattern which has all the entries in the last column of its truth table. We can just say this. We need not say that for all combinations and so on. So a statement pattern which has all the entries in the last column of the truth table as T is called as tautology. If all entries in the last column are F, it is called as contradiction, that is fallacy. And if some entries are true and some are false, it is called as contingency. Now exercise 1.2, third sum. Examine whether each of the following statement patterns is a tautology or a contradiction or a contingency. First, second, third for first, second, third, and then ninth and 10th. These 5 for classwork, remaining for homework. So the first one is what? P and Q implies Q or P. See, the chances are more as far as tautology is concerned, because this is an implication, and implication is false in only one case, when true is implying false. Okay, but of course you have to prepare truth table. See, you have to write this. The first one, first column P, second column Q, third column P and Q, then Q or P, and this is implication. Now I repeat this. It is better that you follow this order only, though it is true that order is immaterial, but follow this order: T, T, F, F, T, F, T, F. Now for this combination, what is P and Q? True, false, false, false. Q or P, it is false when both are false, otherwise it is true. And finally implication. True implying true, yes, true. False is implying true, it may. False implying true, yes. False implying false, yes. Then you have to say all the entries in the last column of the above truth table are T. So P and Q implies Q or P is a tautology. Right down. Second, P implies Q biconditional, not P or Q. First column P, second Q. We need not P only. We do not need not Q. So we need not make that column. Then P implies Q, not P or Q, and finally double implication. So you will notice that all entries in the last column are T. So it's a tautology. Third one, negation P and negation Q or Q. So P, Q, then not P, not Q, not P and not Q, then its negation, and finally its disjunction with Q. So you will notice that entries in the last column are neither all T nor all F. So the statement pattern is neither a tautology nor contradiction. It is contingency. Right on. Now, ninth one, negation P implies Q and P and R. So 3 statements are involved. So how many? 2 into 2 into 2. 8 combinations are possible. So first 3 columns P, Q, R, then not P implies Q, then P and R, and finally their conjunction. So here you will notice that some entries are true, some are false. So the statement pattern is a contingency. 10th one, P implies not Q or R, biconditional, negation of P implies Q implies R. So these are the columns to be made. You will notice that all entries in the last column are F. So the given statement pattern is a contradiction, that is fallacy. Now we are going to discuss important things like quantifiers and quantified statements, duals, negation of a compound statement, and finally, converse, inverse, and contrapositive of an implication. First, quantifiers. A sentence contains one or more variables. A sentence which contains one or more variables is called as an open sentence. An open sentence becomes true or false when we replace the variable by some specific value from a given set. I repeat, an open sentence becomes true or false. I should use the word statement, true or false statement, when we replace the variable by some specific value from a given set. For example, consider an open sentence x plus 4 equal to 7. If x equal to 3, then this sentence becomes a true statement. And if x is not equal to 3, then this sentence becomes false statement. The phrases quantify the variables in open sentences, and therefore they are called as quantifiers. Now there are two quantifiers. The first quantifier is called as universal quantifier. The quantifier for all. The quantifier for all or for every. For every is called as universal quantifier and is denoted by this symbol. Now you may ask me the name of this symbol. This has no name. This is inverted A, capital A, English alphabet. Okay. I repeat, there are two types of quantifiers. Universal quantifier. The quantifier for all or for every is called universal quantifier and is denoted by inverted A. The second quantifier is called as existential quantifier. Existential quantifier. The quantifier for some or for one or there exists at least one or there exists is called existential quantifier and it is denoted by this symbol. This is mirror image of English capital letter E. So if the words like there exists at least one or for some, SOME, or for one, if these occur in a sentence, okay, then it is called as existential quantifier. And what is quantified statement? An open sentence with a quantifier becomes a statement. Such a statement is called a quantified statement. I repeat, an open sentence with a quantifier becomes a statement. Such a statement is called as quantified statement. So this is about quantifiers. Then this is comparatively simple one. Concept of dual. Two compound statements S1 and S2 are said to be duals of each other if one can be obtained from the other by replacing, see on the screen, by replacing or by and by or. That is by interchanging the symbols for in conjunction and disjunction. For example, we have done this in set theory, De Morgan's laws. Negation of P and Q is negation P or negation Q. Now its dual will be what? Negation P or Q is equivalent to negation P and negation Q. That is, you will notice that symbols for conjunction and disjunction are interchanged. I hope this is clear to you. Now this is referred to as duality of conjunction and disjunction. Statement patterns 1 and 2 are called duals of each other And as I have told that these are also called as De Morgan's laws. If a compound statement S contains T, that is tautology, or F, that is contradiction, then the dual of S is obtained by replacing T by what? F, and F by T. So in short, you have to interchange these symbols and by or and vice versa, and capital T by F and vice versa. Okay, so this is nothing but rather this is about duality. So what is principle of duality? If a compound statement S1 contains only negation and or, and statement S2 is obtained from S1 by replacing and by or by and, then S1 is a tautology if and only if S2 is a contradiction, obviously. Okay. Now, negation of compound statements. This is very important. Actually, you have to remember this. We claim something and we prove that by constructing truth table. So we are going to discuss negation of conjunction, then negation of disjunction, then negation of implication, negation of biconditional, and the simplest part is negation of negation, which is nothing but original statement. I repeat, we are going to prove these statements for negation. How? By constructing truth tables. The first one, negation of conjunction is disjunction of negations. I repeat, the negation of conjunction of two statements is the disjunction of their negations. Let me list negations first, then we will verify. Second, negation of disjunction. Can you tell me the formula or rule rather? Instead of formula, I should say the rule. Yes, it is conjunction of negations. We have discussed this in duals also. These are Morgan's laws. So negation of disjunction is conjunction of negations. Now the third rule, you have to remember this as it is. Of course, we are going to verify this by constructing the truth table. Then comes negation of implication. Negation of P implies Q is P and not Q. Now you will ask me, sir, tell me the logic for this. The logic is we construct the truth table and we say that entries in the last column are identical and therefore negation of P implies Q is P and not Q. Now if you remember this, then you can easily obtain negation of P by conditional Q. I'll tell you how. First, let me write the negation. It is P and not Q. Okay. It is P and not Q, or Q and not P. I'll tell you the reason behind this. Basically, why biconditional? Because it is P implies Q and Q implies P. Here you will notice that in case of biconditional, P implies Q and is implied by Q. So P implies Q and at the same time Q implies P, hence the name biconditional. So negation of this is negation of this. Now basically this is conjunction. What is negation of conjunction? It is disjunction. See, disjunction of negations. Now what is negation of P implies Q? P and not Q. We have just written this. And what will be the negation of Q implies P? It will be Q and not P. Is that clear? So this is about negation of biconditional. And the simplest one is negation of negation. What is negation of P? It is nothing but P. So negation of negation is nothing but original statement. As I said, the results can be proved by constructing truth table. See the negation of conjunction. We have just defined, or in fact we have written that what is negation of P and Q? It is not P or not Q. See the table is constructed. P, first column P, second Q, then P and Q, its negation. Then we need not P, not Q, and finally not P or not Q. The entries in columns 4 and 7 are identical. So not P and Q is not P or not Q. Thus we see that the negation of the conjunction of two statements is the disjunction of their negations. So I don't think this will be asked in board exam, that prove that negation of conjunction is disjunction of negations. But if asked, then you have to prove this by constructing this truth table. Now this is an example. You can go through this afterwards. Negation of disjunction. Again, truth table. See, the entries in columns 4 and 7 are identical. So they are logically equivalent. That is, negation of disjunction is what? Conjunction of their negations. This is again a De Morgan law. I have already uploaded this file. Negation of negation. This is the simplest one. If P is true, not P is false, and again its negation is true. So negation of a statement is that statement itself. Yes, negation of implication. So not P implies Q is P and not Q. This is the table. So entries in column 4 for negation of P implies Q, and column 6 for P and not Q are identical. So they are logically equivalent. Negation of biconditional. I have already explained how to remember this, but you can verify this by constructing this truth table. I repeat this part. Basically, why biconditional? Because it is double implication. P implies Q and Q implies P. So negation of biconditional is negation of that conjunction, which is disjunction. See the cursor. Disjunction of negations. Negation of what? P implies Q. It is P and not Q. And what is negation of Q implies P? Q and not P. So this is how you have to remember this table, rather this result, and can be verified by constructing truth table. Okay, now this is very, very important. Please listen to me carefully. Negation of quantified statement. The negation of quantified statement is obtained by replacing the word all by some, for every, by there exists, and vice versa. Note that negation of a statement pattern involving one or more of the simple statements PQR and one or more of the free connectives and or negation is obtained by replacing and by or by and PQR by not P, not Q, not R respectively. This is the example of negation of the statement pattern. Okay, so this is very important, especially negation of quantified statements. You have to be very careful obtaining negation of quantified statements. Now, this is again an important part. Some can be asked on this, write the converse, inverse, and contrapositive of the given implication. So, see, this is defined. If P implies Q is a conditional statement, then Q implies P is called as its converse. Not P implies not Q is called its inverse. And not Q implies not P is called its contrapositive. I repeat this part. If P implies Q is a conditional statement, then Q implies P is its converse. not P implies not Q is its inverse, and not Q implies not P is its contrapositive. So by constructing truth table, we can verify that conditional statement, that is implication, is logically equivalent to its contrapositive. I repeat, an implication is logically equivalent to its contrapositive. So this is an important part. Exercise 1.3. First question, if set A contains 3, 5, 7, 9, 11, 12, determine the truth value of each of the following. Number 1, there exists at least one x belonging to A such that x minus 8 is 1. Actually, x minus 8 equal to 1 means x equal to 9. Does 9 belong to A? Yes, it does. So you have to write this. You can't just say that statement is true. You won't get full marks for that. You have to say that clearly for x equal to 9. Now this is important. See, if 9 doesn't belong to A, then the statement will not be true. So for x equal to 9, most importantly, it belongs to A, set A, satisfies x minus 8 equal to 1. So statement is true. So what is the truth value? It is nothing but T. Right now. Then second, for all x belonging to A, x square plus x is an even number. You can verify. Basically, question doesn't arise in case of even number. But for an odd number also, you can say that take x common to get x plus 1. So an odd number immediately followed by even number. Their product is going to be even number. I hope you are getting this. Or in answer, you may just write for each. Right now, you can verify individual element. For each x belonging to A, x square plus x is even. You can verify this. Therefore, statement is true. Statement is true. Its truth value is T. Right now. So third one, there exists at least one x belonging to A for which x square is less than 0. Now, how can a square be negative? So this is false statement. Its truth value is F. Fourth one, for all x belonging to A, x is even. Now every number except 12 in the set A is odd. So statement is false. So truth value is F. Fifth one, there exists at least one x belonging to A such that 3x plus 8 is greater than 40. You can cite one example only. But here you will notice that for x equal to 11 and 12 also, 3x plus 8 is greater than 40. So statement is true. Truth value is T. Now, sixth one, for all x belonging to A, 2x plus 9 is greater than 14. Just check for the smallest element 3, all are positive. So for 3, you will notice that 6 plus 9, 15 is greater than 14. So must be true for remaining also. So the statement is true, though it is universal quantifier. It is true. So the truth value is T. Second question, write the duals of each of the following. Now, don't write answer directly. For example, first one, we have to write the dual of P or Q and R is P and Q or R. What is dual of P and Q and R? It is P or Q or R. Third one, dual of P or Q and R or S is what? P and Q or R and S. See, these are the answers for 4th, 5th and 6th. Yes, these are the answers. 4th, 5th, 6th, 7th. See, you have to be very careful. In sum number 8, C is to be replaced by T. In 9th, T is to be replaced by C in dual. And in 10th also, C is to be replaced by T. So these are the answers. Now, third question. This is very important. Write the negations of the following. First one, x plus 8 greater than 11 or y minus 3 equal to 6. So you have to define two statements. Let P be the statement x plus 8 greater than 11. So it will be not P, x plus 8 not greater than 11. You may also say x plus 8 less than or equal to 11. But why to say that? Negation of greater than is not greater than. Q y minus 3 equal to 6, not Q y minus 3 not equal to 6. Okay. Now given statement is P or Q. What will be its negation? So you have to write everything if you want full marks. Given statement is P or Q. Its negation is not P or Q, is not P and not Q. That is x plus 8 not equal to 11 and y minus 3 not equal to 6. Second is for homework. This is the answer. Third one is important. Quadrilateral is a square if and only if it is a rhombus, means it is biconditional. So we define two simple statements. Let P denote quadrilateral is a square. So it will be not P. Quadrilateral is not a square. Q, quadrilateral is a rhombus, not Q. Quadrilateral is not a rhombus. So symbolic form of the given statement is P biconditional Q. So what is negation of this? You should be able to write this directly. P and not Q or Q and not P. Please do not use the word if not in this case. So quadrilateral is a square but not a rhombus. Instead of but you can use and also. Quadrilateral is a square and it is not a rhombus. Or quadrilateral is a rhombus but not a square. Again, instead of but you can use and. Okay. So that's it for today.